I'm Audrey Cheng, a third-year PhD student at UC Berkeley, as well as a part-time engineer at Meta. Today I'm recording from Meta's Menlo Park offices, and I'm excited to tell you about RAMP-TAO, a novel protocol layering atomic transactions on top of Meta's online TAO data store. This project was a collaboration between academia and industry, and it was also presented as a paper at VLDB 2021, where it won the Best Industry Paper Award. So, to start off, the social graph underlies many diverse products at Meta, including some of the ones we see on the right-hand side. As such, it operates at huge scale, serving tens of billions of reads per second, as well as tens of millions of writes. Given the challenging workload, there are multiple guarantees that we want to enforce on the social graph. As an example, consider a social media user, Alice, who's a musician, and she wants to create a post with both her recording and sheet music for a new song she's composed. Without any guarantees, there's multiple things that could go wrong. First, without read-to-write consistency, it's possible that Alice wouldn't be able to view her post immediately after creating it. Also, we want to ensure that Alice has both her sheet music and recording visible. We need failure atomicity, which ensures that all parts of a transaction are either committed or aborted. If another user, Bob, tries to view her post, we want to ensure that he sees either both her recording and sheet music or neither. We need atomic visibility, which ensures that all or none of any part's transactions are visible to other transactions. These are the sorts of guarantees we need on the social graph to hide anomalies from product developers. Given the range of products sharing data on Meta's social graph, there are many complex interactions that further motivate the need for these guarantees. In particular, one application's behavior shouldn't affect the behavior of others. In this talk, we'll cover how Meta ensures these guarantees through its system and how this system has grown and evolved and what its needs are, as well as the impact of the lack of guarantees, which we quantify in the first large-scale measurement study of its kind. And finally, we'll talk about our novel RAMP-TAO protocol, which ensures stronger guarantees at scale. So TAO is Meta's online social graph data store, and it presents a simple graph API to do a few things well at scale. TAO consists of graph-aware cache layers that overlie statically sharded MySQL instances, and it was originally designed to be eventually consistent to provide high availability and low latency. More information can be found in a 2013 ATC paper. As the system has matured over the last decade, there has been growing needs for stronger consistency and isolation guarantees. In particular, this has been motivated by product developers directly accessing the system to using a higher-level query framework called ENT that makes it easier to express complex operations on the social graph. These high-level operations can generate many sub-requests to TAO, and the lack of guarantees between these operations can lead to anomalies that product developers have to explicitly handle. However, these issues are often hard to reason about and debug, but they must be handled to prevent end-user impact. While there's a strong need for these guarantees, there are significant challenges to adding them to the system. First of all, we require low performance and storage overheads, since we're dealing with very skewed data that's a very high volume and also petabytes of data per day. Additionally, we don't want to impact the applications that don't need these guarantees and only want the applications that require them to bear the resulting performance and storage costs. A strawman solution could be to overhaul TAO's replication protocol and enforce these guarantees synchronously, but this would lead to unacceptably high overheads. Meta's strategy has been to layer these guarantees on top of the system to retain its reliability and efficiency. For read-to-write consistency, there is now a system called Flight Tracker that ensures this guarantee for TAO as well as other data stores, and more information can be found in a 2020 OSDI paper. For failure atomicity, write transactions have been added to TAO, and we'll cover these briefly. So there are two cases of write transactions on TAO. If all the data is on a single shard, TAO relies on MySQL to guarantee failure atomicity. But this is not always feasible for some applications. So in the other cases, we have cross-shard writes, which use two-phase locking and two-phase commit and assign a unique ID and logical timestamp to each transaction. There's also a background recovery process for failures. Finally, for the third guarantee we mentioned, atomic visibility, this was an open question before this work, and it is what we'll focus on in this talk. So first, we'll explore what happens without guarantees. And in do so, we perform the first large-scale measurement study of its kind to quantify the impact of atomic visibility. To do so, we proceed in 3 steps. The first one is to model production data, because previous to this, there were no read transactions on TAO, so we needed to model these read transactions, and then we generated this workload and then checked for anomalies. So on the read side, we looked at end queries, which essentially have multiple subqueries to TAO and represent the read transaction boundary that TAO developers are looking to support in the long term. Specifically, we looked at the number of operations and the number of data items in these queries, which we're showing the distributions of on the right-hand side here. And we see that for the most part, these queries are pretty small and limited to less than 10 operations and distinct data items, but there is a relatively long tail, in which some cases the queries can span over 100 items. On the right side, we look at end change sets, which capture simultaneous writes to TAO and the transactional intent for writes. We also see a similar trend in this data. Most of these change sets involve just a couple of operations and data items, but there are cases in which there can be many items involved. For workload generation, we accurately model these workloads using the probability distributions we showed earlier, and the benchmarking framework that we used is now available in open source at taobench.org, and it was also published in a VLDB 2022 paper. And the workloads we used, as well as other workloads, are also available. Finally, to check for anomalies, we basically wanted to look for atomic visibility violations, which are read transactions that observe partial write transaction results. So to do so, we basically fetch the most recent write set for each item we're reading, and then we check if all those versions are all the valid versions we need are present. So how much does atomic visibility actually matter? We found that 1 in every 1,500 naively batched reads violates this guarantee. While this figure might seem small, its rarity is actually a source of complexity. When we dug deeper, we looked at the duration of these atomic visibility violations, and we found that they could span up to 30 seconds, which is quite significant considering we're doing billions of reads per second. Furthermore, we found that some of these violations could not be easily fixed with repeated retries. So we found that there were 2 types of violations. The first type are ones that we could resolve with repeated reads. These represented 45% of the violations. And in these cases, you'll notice the line in orange showing that the time between the read and write transaction start was relatively small. And these cases are due to the read and write operation racing each other. On the other hand, the yellow line represents 55% of violations in which these write transactions have actually failed and are undergoing the recovery process, so the reads cannot be fixed in a timely manner. I want to make an additional point here about rarity at scale, because as we see, even though 1 in 1,500 might sound very small, if you're doing billions of queries per second, this is actually quite significant in practice. And furthermore, because it's not very common, this adds additional complexity for product developers who need to go and find these bugs that are not deterministic, and these rare issues are often hard to investigate, reproduce, and debug. So, seeing the need for atomic visibility, we first turn to the RAMP protocols, which are the only algorithms we're aware of that specifically ensure this guarantee. However, there are several challenges to applying them directly to TAO, which we'll cover. And then we'll introduce our novel RAMP-TAO protocol and explain how that's able to ensure atomic visibility at scale. And finally, we'll describe several optimizations that allow our protocol to be feasibly deployed in production. So the RAMP or Read Atomic Multi-Partition protocols are ones that ensure atomic visibility, and they operate in 3 stages. There are more details in a VLDB 14 paper on this, but I will give a brief overview of how they work. So let's say we have an application in a database, and here we have two keys, X and Y, and they're stored on different shards. We also store the right transaction set for each key. So here we have transaction A that's written X1 and Y1, and transaction B that's written X2 and Y2. Notice here that while X2 is on shard 1, shard 2 hasn't yet been updated with Y2. So in this case, let's say the application wants to read X and Y. It will try to fetch that from the database, and the database will return the most recent version along with its corresponding right transaction metadata, and then we'll check to see if any of the versions are missing using the metadata we fetched. In this case, we see that we need Y2 because we've read X2, so we also need Y2 to ensure atomic visibility. So we'll go and send a second round read requesting Y2, and now our shard 2 has been updated with Y2, so that data is available, and we're able to return an atomically visible result once we've gotten Y2 from the database. There are several key benefits of RAMP that merit its potential use on TAO. First of all, RAMP reads don't require coordination and are non-blocking, so they would have minimal impact on non-transactional workloads. Also, the size of the metadata required is bounded to the most recent write set of each key being read. And finally, RAMP's write protocol is very similar to TAO's write transactions, so there would be minimal changes required for writes. While the RAMP protocol seems promising, there are three significant challenges that prevent it from being directly applied to TAO. The first one is that it requires the metadata for each write transaction to be stored for each key, but doesn't consider the replication caching in our system, which, if we were storing all that metadata, would lead to unacceptably high storage overheads. Furthermore, RAMP requires multi-versioning to guarantee read termination. So in our previous example, we needed Y2, but let's say that Y2 was actually overwritten by Y3, and we don't support multi-version currently in either the database or the cache. So when the application tries to read Y2, that value is no longer available and the read cannot terminate. Finally, the third challenge is that RAMP only considered requests to the database, but we also have a cache, which is very essential for our system because that ensures low latency and hotspot tolerance, and that needs to be taken into account when applying RAMP. Now we'll go over our novel RAMP-TAO protocol, which overcomes the three previous challenges mentioned. And our key insight here is that we only need to ensure atomic visibility for recent transactionally updated data. This is because data that isn't written to transactionally, first of all, is atomically visible by default. Given that only 3% of TAO's current workload is involved in write transactions, most of the data can be returned immediately to the client. Also, under TAO's eventual consistency, once everything has been replicated and there are no new updates, then the data is also atomically visible. So we leverage this insight to minimize the performance and storage overheads of our protocol and serve most reads locally. And specifically, we use the refill library, which is a metadata buffer for writes within TAO that already exists. So now I'll go through the RAMP-TAO protocol with several examples to provide the intuition behind this algorithm. So here we have a setup with our application, our TAO cache, and the refill library within the TAO cache. The refill library, previous to this project, was meant to store the past 3 minutes of all write data. And we also have the database here with two shards, and we have keys X and Y on the two shards. And you'll also notice that instead of storing the key in the transaction metadata, we're only storing the shards to reduce the amount of storage overhead. So the first modification we make is that we have the refill library also store limited transactional metadata. So only for the past 3 minutes do we store both the keys for each transaction, and we also mark each key that's been updated transactionally in the recent path with a bit so that we're able to check for this. So now when the application does a read to TAO, TAO will return the most up-to-date version as well as its corresponding write transaction metadata if it is present. And we're able to take this metadata and check if any versions are missing. And here we see that we're missing X8 because we read Y8. So we need to go and fetch that version because the current result does not satisfy atomic visibility. In the meantime, let's say another write transaction occurs. So both X8 and X9 and their corresponding write transaction metadata are sent to the TAO cache. And we also add limited multi-versioning within the refill library so that we have the versions we need in the case we need to satisfy atomic visibility. So now the application tries to read X8, and that's available because we have multi-versioning, and we're able to return an atomically visible result. Most read transactions on TAO can actually take the fast path under RAMP-TAO, which means that basically you only need one round of communication with the local cache. So let's say 5 minutes have passed. At this point, the older versions as well as the write transaction metadata have aged out of the refill library. So we only have these versions available, but we know that if an application asks for any of these keys, the results will be atomically visible by default since these haven't been updated recently. So the versions that are there do satisfy this guarantee. Also describe a optimization for bidirectional ASOCs or associations, which are basically paired edges in the social graph. These are important to consider separately because they're very common on TAO. They consist of 52% of all edge types as well as 56% of the edge write volume. On the right side, they are considered a special type of write transaction because they don't need to undergo two-phase commit if there are no preconditions or integrity constraints, these edges. And there's also a background process that fixes failures. The guarantee we need to ensure here for atomic visibility is that the data and the paired edges should be the same. So when they're read, all we need to do to ensure atomic visibility is to replace the older version with the newer one in the inverse if the versions mismatch. And this ensures that the reads will always be local, so we can always finish in one round, which is very important because these represent a large volume of reads. We show that RAMP-TAO can be feasibly deployed in production. Specifically, we look at the latency of RAMP-TAO and compare it to current TAO latency. We find even the tail latency is very similar. And furthermore, we're able to serve over 99.9% of reads in one round. And the memory overhead of our protocol is limited. As we work to add stronger guarantees at large scale, there are several important lessons we took away. The first is that we should only ensure stronger guarantees when necessary. The second is that the read and write availability can affect each other and need to be considered carefully. And finally, we delve into several key techniques in working with read-optimized systems. So we find that it is very essential to ensure that only the applications that need stronger guarantees bear the costs of using them. We shouldn't affect the vast majority of applications that don't need these guarantees. We're able to achieve this by layering RAMP-TAO on top of the system to isolate the impact of adding atomic visibility. And there is an additional benefit here in that we limit changes to a mature infrastructure. Also, read and write unavailability can impact each other. So in our case, we have Flight Tracker, which ensures read your write consistency, and this tends to advance versions more quickly. As a result, this can amplify the effects of write unavailability. So if there's a version that RAMP-TAO needs to read to ensure atomic visibility, this might not be available yet. And the short-term solution is that we can roll back these write transactions we're waiting on so that reads aren't stalled. And the long-term solution is to add full multi-versioning to the underlying database, which is currently in progress. Finally, in working with read-optimized systems, there are two parts essentially for guaranteeing stronger consistency and isolation. First of all, we need a staleness check of local data because we need to be able to serve most of the requests from the local cache. Only in rare cases should we need to go cross-region to fetch any missing pieces. RAMP-TAO also follows this structure. We first have that local check for atomic visibility after our first round read, and only in rare cases do we go cross-region if certain versions we need haven't yet been replicated to our local cache. In conclusion, we've presented a layer approach to provide stronger guarantees at scale, and our key insight in focusing on recent transactionally updated data allows us to feasibly deploy RAMP-TAO in production. Future work will look at further strengthening guarantees, such as considering stronger isolation levels like snapshot isolation. In the meantime, we've open sourced the workloads we use in this project, as well as the overall TAO workloads at taobench.org. And these workloads, as well as the benchmark, has already been used at Meta, as well as other databases such as Cloud Spanner, CockroachDB, PlanetScale, TiDB, and UGAbyteDB to identify performance opportunities and bugs. So we encourage you to check us out at taobench.org and reach out for further questions. Thank you very much for your attention.